I'll now come to the combinatorial interpretation of a derivative. So let's just jump straight into the definition, and then we look at some examples. So let me define the derivative of a species. So let F be a species of structures then its derivative, which we usually denote by f prime or d dx fx using the calculus notation, is the species f prime of u for every finite set u is f of u plus, where u plus is the set u with one point adjoined to it. The point we'll denote by star. And if we want to be a little more specific about which set we are adjoining the point to, we may use a subscript star, subscript u. And transport of structure is defined by, if you have a bijection sigma from u to v, you define a bijection sigma plus from u plus to v plus by sigma plus of u is just sigma u if u belongs to u, and sigma plus of star u is just star v. Then transport of structure is defined by f prime sigma of u is f prime sigma of s is f sigma plus of s for every s in f prime. So we can visualize this as follows. Suppose we have a set then an f prime structure on this set is the same as putting an f structure on this set with one point, which we call star, attached. Another visualization is the following. Suppose you have a set f and you have an f prime structure on it. This is the same as putting an f structure on, let's see, on this set with one additional point attached. And this additional point has no particular special position in the f structure. It's just one new point, and that is reflected by putting this in a sort of random place in U. Let's look at a quick example. I claim that L, the species of linear order structures, is the derivative of the species of cycle structures, and I can give you a proof without words. So the derivative of the species of cycle structures is given by this picture here. So we have to take a set and we have to add a point star to it, and we have to put a cycle structure on the set union star. So that looks something like this. and this is C prime. This star is not a point in U, this is the added point, and this is of course the same as what is happening on U. Well, let's remove this added point. And what we're left with here is just a linear order. And so C prime is equal to L. If you want, you can try to write a formal proof of this, describing exactly how to get the isomorphism of species using bijections. And what does derivative do to generating functions? So it's quite simple. So I guess the main thing is to figure out what happens to the cycle index generating function, and everything follows from that. So if f is a species of structure, then zf prime x1 x2 is del x1 zf x1 x2. The type generating function of f prime is just given by, well, we can just get it from here. It's del x1 zf, but then you have to substitute x squared, x cubed, and so on. So it's not much of a simplification, but what's really beautiful is for the exponential generating function f prime x is, well, it's just the derivative of fx, and that's quite clear from 1. So in fact 1 implies 2 and 3. That's completely clear. So we only have to prove 1. The main point in the proof is that if you take f prime n and look at its fixed points under sigma, well, by definition that's the same as the fixed points in n plus 1 of sigma plus, where I think of sigma plus as the permutation sigma extended to n plus 1 by just taking n plus 1 to itself. So sigma plus of n plus 1 is equal to n plus 1. Sigma plus of I is equal to sigma I if I belongs to n. Now note that the sigma plus 1, it has one more 1 cycle than sigma, and it has other k cycles are the same as for k greater than or equal to 2, the number of k cycles in sigma plus is the same as the number of k cycles in sigma. And so what we get is therefore sum n greater than or equal to 0, 1 over n factorial, sum sigma in Sn f n plus sigma plus times product I greater than or equal to 1 xi raised to sigma I. Well, we've already seen how we can write this as a sum over partitions n greater than or equal to 0, 1 over n factorial, and then we write a sum over partitions. And what we have is f. So let's say alpha is a partition 1 raised to a1, 2 raised to a2, and so on. We'll write alpha plus for the partition 1 raised to a1 plus 1, 2 raised to a2, and so on. But anyway, a priori this is f of n, f prime of n, and then the number of invariants, or maybe we can just write it as f of n plus 1, number of invariants under a permutation sigma plus, which will have cycle type alpha plus if sigma has cycle type alpha. So So maybe I'll say sigma alpha, where sigma alpha is a permutation with cycle type alpha. And then we'll have the number of permutations with cycle type alpha. So that's n factorial divided by product over I raised to ai factorial, and then we'll have product x sub I to the power ai. But if you think about it, this is just sum n greater than or equal to 0. This n factorial and this n factorial cancel out. What you get is sum over alpha partitions of n. But if you think about it, this is the same as del x1 of sum over all alpha partitions of n plus 1 f n plus 1 sigma times 1 over. The point is this x1 raised to a1 gives an a1 times x1 raised to a1 minus 1, and so this is actually just product I raised to ai factorial, but this is just del x1 zf x1 x2. So the cycle index generating function of zf prime, this is what it is the derivative, partial derivative with respect to x1 of the cycle index generating function of f. Okay, let's look at some more examples. Here's a very simple example which makes the connection with the differentiation of polynomials. So x prime is equal to 1. Well, why is that? So x prime of u is x of u plus, and so we want u plus to be of size 1. Which means that u is of size 0. And empty otherwise. And this is isomorphic to the species 1, which takes singleton u if u is of size 0. And similarly, you can show that 1 prime is equal to 0. What about derivative of x to the n? Well, it turns out that x to the power n is isomorphic to ln, where L is the species of linear orders and ln is just its degree n part. So remember, ln of u is linear orders on u if cardinality of u is n and it's empty otherwise. So what is an ln prime structure? So that's a linear structure on a set which together with star has size n. So we have a set of size n minus 1 and then we add a star to it. So an ln prime structure looks something like this. So we have a star somewhere. Maybe the star is the least element in our linear structure. And we have 1, 2, 3, dot, 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 n minus 2, n minus 1. So this set has totally size n. But it could also be that the star occurs in the second position. So we may have something like this. The 1 is over here, the star is over here. Or we may have something where the star is in the third position. So we have 1, 2, star, something like this, and so on. All the way up to where the star is in the last position. But if you ignore the star in each of these diagrams, then you get that each of them is just Ln minus 1. But there are n of these diagrams, so we get Ln minus 1. So what we have is d dx x to the n is n times x n minus 1. Here's another example. What if you take all of L? What is its derivative? L prime is actually L dot L, which I can write as L squared. I'll give you a proof without words of this. What is an L prime structure? Well, you have to take the set U, add a star to it, and put a linear order on that. So you may visualize that as something like this. So you have so this is an L prime structure. But now if I take this and remove the star, what am I left with? Well, I have the set which is divided into two parts, a first part and a second part, and on each part I have an L structure. So this is the same as L squared. So L prime is equal to L squared. Let's look at another example. I'll define a species called partial partition structures. So par P is defined as E dot par. What this means is that you remove a certain subset, so it looks like this. You remove a certain subset and put an E structure on it, and on the remaining you put a partition structure. So what it amounts to is that you're taking a subset of your original set U and you're putting a partition on it. So par PU is this partitions on subsets of U. But this is the same as I can just it's like a set partition where of course this part can be empty also, but I can think of this part as a distinguished part. So what I can do is I can think of this like this. I can put my star over here. Well, why not just copy this picture here? I can add my star to E, and what this now this E is forced to be this component of U plus, this block of U plus is forced to be non-empty because at least star is in it. And so what we have is this left hand side is par P and the right hand side is par prime. So what we have is E dot par, which is the same as par P, is par prime. And this has some interesting consequences for generating functions. We get par P x is ddx e to the x minus 1, but that is also the generating function of E dot par, which is e to the x times e to the power e to the x minus 1. But you can also check this identity in calculus using the chain rule, but here is a combinatorial proof of this. If you ask about the cycle generating series, well, it's going to be x of x1 plus x2 by 2 plus x of summation k greater than or equal to 1 over k x of x1 plus x2 by 2 plus, oops, I'm running out of space here, minus 1, I guess. This should be xk plus x2k, which you can again check by using calculus. And par tilde p is just 1 over 1 minus x times product k greater than or equal to 1 over 1 minus x to the k. Or if you wish, you can write this as 1 over 1 minus x squared times product k greater than or equal to 2 1 over 1 minus x to the power k. Okay, here's another nice example. E is its own derivative. I'll leave that one. It's easy. I'll leave you to give a combinatorial proof of that. Okay, what about higher derivatives? So we can define f0 to be f, f1 to be f prime, and so on. In general, the kth derivative of f is the derivative of the k minus first derivative. A visualization of f3 in f3 structure is the same as adding 3 star points. So you take an F structure, but then you add 3 star points, which we'll call star 1, star 2, and say star 3. So what we can say is that fk u is f of u plus k, where by u plus k I mean u disjoint union star 1 star 2 star k new points which are distinguished from each other. Example, the kth derivative of L is k factorial L to the power k plus 1. You can work this out using induction and see that this is true. I'll leave it as an exercise. Here's another interesting example. So remember that this A, lowercase factor A, is the species of trees, and this uppercase A is the species of rooted trees. Now I claim that the derivative of trees A prime is an ensemble or an assembly of trees, of rooted trees. And I'll give you a proof without words of this identity. So suppose you have an element of A prime. So what does that look like? So you have a tree structure on a set. I'll put the star at the bottom this time with a star added to it. So it may look something like this. Okay, so this is an A prime structure. And let me show you why it's the same as the right hand side. So you remove the star, and what are you left with? Well, you're left with these three trees, but also these trees are rooted because when you remove the star, there was one node in each of these trees that was connected to the star, and we'll think of that as the root. So A prime is the same as an assembly of rooted trees, or what you could call a forest of rooted trees.